Next problem is similar. It says the focal length of a converging lens is 10 centimeters. What is the magnification of this lens viewed by a relaxed eye with a near point of 25 centimeters? So again, relaxed eye means same thing as eyes, focused in infinity. So this is focal. This is near point over focal length of the lens. So near point is 25, and this is 10, so this is 2.5. Now let's say you were to look at this by, let's say it was strained vision, just for sake of practice. Right? If you were to do strained vision, then try that on your own. It's pretty simple. So it'd be near point focal length, which 10 centimeters plus 1, that just comes out to 3.5. Very simple. Okay. So what is the maximum possible magnification of the converging lens of focal length 5 centimeters? So again, we have magnification, and we have near point, and we have focal length. Now, they're asking what is the maximum possible magnification. So you might be wondering, okay, well, we're only given the focal length here. What do? We know that we can use this equation for relaxed vision and get a certain magnification. But we also know that we can use strained vision and actually get a higher magnification. And since we're looking for the maximum possible magnification, we want to use this equation because it will give us a higher magnification given the same near point, same individual, same near point, same lens. So we want to use this one. Now, the near point, again, what do we plug in? We're not given anything. Generally, when you're not given anything for near point, it's going to be 25 centimeters. That's the near point of most people who don't have nearsightedness. And we're set the focal length is 5 centimeters. So, and the 1 for strained vision. So this comes out to 5 plus 1, 6. Right, so 6 is the maximum magnification of this lens. Excuse me. All right. A certain astronomical telescope has a diameter of 5.6 meters. What is the maximum angle of resolution for this telescope at a wavelength of 620 nanometers? So this uses a certain formula which we'll get into. This is called resolution. So if you're looking at something and it's coming toward your eye, let's say we have a light source here, right? 2 points very far away, and your eye is trying to see what's going on. When they're so far away, it's actually going to be kind of difficult to tell the 2 points apart, right? Even though in the equation for the lens equation, not the lens equation, but this equation, for people who have normal 20/20 vision, we say that their far point is infinity. So we say that this is infinity. But the reason it doesn't really work is because if something is really far away, your eye can't tell 2 points apart, right? It's going to have a hard time doing this. So we're going to have what's called a minimum angle of resolution, meaning how far away our 2 points have to be in order for you to be able to tell them apart. So it's going to look something like this. We have 2 points, and I'm drawing them very bad here. Let's draw them a little better. And they're going to be a certain distance from your eye. And they're both going to send light directly to your eye. They're going to have their light rays that converge on your eye, they're going to have a certain angle. And this light right here has a light isn't go straight, but we just model it this way. Light is a wave, right? And it's going to have a certain wavelength. And then there's going to be the diameter of your eye. That's another variable in this equation, diameter of your eye. Depends on your kind of what is that part of the eye called? The pupil, right? The pupil, yeah. So the diameter of the pupil, or if it's in this case it's a telescope, so that of a telescope. The way in which these variables are related is here. Right. So the angle between them, so this, is equal to 1.22 times the wavelength of the light over the diameter of the eye, or the whatever instrument you're using. This is only going to be the case when you can actually tell the 2 points apart, right? If you can't tell the 2 points apart, the resolution is too low. This is not going to apply. But this is actually not the minimum, but the maximum angle of resolution. So in this case, we can just solve. It's pretty simple, plug and chug in a sense. And keep in mind something else. This is going to be in radians. So if you're using your calculator and doing any sine stuff, convert this to degrees first, or use a radian on your calculator. So they're asking for the angle of resolution. We have wavelength at 620, but again, 620 nanometers. 620 nanometers is equal to 620 times 10 to the negative 9 meters. And then this diameter, we're told the diameter of the telescope is 5.6 meters. So 5.6 meters. So this is going to be a pretty small number. So it's going to be 1.3507 times 10 to the negative 7 meters, right? Not meters, I'm so sorry. This is an angle, radians, not meters. That's this angle. So if two stars are very, very far away from us, the maximum angle they can make and still be clear is this. Right? It's that many radians. What is the limiting angle of resolution? Limiting angle of resolution, again, means same thing, that angle that you need to be able to resolve 2 points. Limiting angle of resolution for the eye. If the pupil diameter of the eye is 4 meters, a wavelength of light 600 nanometers, and an index of refraction for the eye equal to 1.34. Excuse me. So, again, using that equation, you want the angle again, and we have a certain wavelength. Now, the wavelength of light that enters the eye is going to be a little different than the wavelength of light that we're given here. We're given 600 nanometers, but we're told that the index of refraction of the eye is equal to 1.34. So when, as we talked about in the last video, whenever you have the index of refraction of something equals the speed of light over the speed of light inside the medium. Right, this is speed of light in the vacuum. Now, why does the speed of light decrease when we go through a substance that's not vacuum? It's because the wavelength of light changes, not the frequency. The frequency is always the same. So here's how you relate those two. So the equation is the wavelength of light that's just in vacuum equal to the index of refraction times the wavelength of light in the medium, right? And M means any medium you have. So in this case, the medium is the liquid inside the eye, right? Because the index of refraction of the eye is equal to 1.34. So, excuse me. So, if you rearrange this equation, you can see we can put the index of refraction of the eye on the bottom. So this is index of refraction. This is the wavelength of light in the vacuum, and this is the wavelength of light inside the eye. That's what we want to put here, not for this. So we are going to put the wavelength of light in the vacuum over the index of refraction, which is 1.34. And the wavelength of light in vacuum is 600 nanometers, so that's 600 times 10 to the negative 9. And the diameter of the eye is 4 millimeters. So 4 times 10 to the negative 3 meters. So if we do this, so that is the angle of resolution. A person with myopia has a far point of 66 centimeters. What is the power of a spectacle lens that would give him a normal far point? Myopia means nearsightedness. So they want a normal far point. So they want them to be able to see something that is infinitely far away. So they want to see objects that are infinitely far away. So the distance to the object would be infinity. Normal far point, again, is infinity. Distance from the image, we want to project the image onto their far point, right? And their far point is 66, so the image is going to be 66 centimeters away. But keep in mind a couple of things. So first, you don't want it to be in centimeters, you want it to be in meters. And the image is always going to be a virtual image, so this has got to be negative. So when you take into account all that, this power here equals negative 1.515 diopters. So that's it for this video. I hope you learned how to do these problems. Thank you for watching.